spend too much time, and because we don't have enough time also. So let's take a look. I want to look at 3 papers and also 1 video. How people do the experiment, cryogenic experiment for FinFET. Okay. Why cryogenic? Increase the mobility. You are okay with this? Why you have a higher mobility at cryogenic again? Anyone can tell me? Photon scattering, yeah, mu photon will increase, right? It also increased the velocity saturation. We talked about that before also, but I mentioned very fast flying over the slide, but just remember it increased. We don't need to know the physics, right? Now that's one thing though. I talked about undoped channel. I just want to emphasize one more time. This is something you should know very well. In a typical MOSFET, maybe you have 1E21 or 1E20 of source string doping, and then here maybe 1E18. If you goes to 45 nanometer, right? The one we're doing 65 nanometer is like 5.5 E17, right? Yeah. So, but in FinFET, it is like this. 1E21, 1E21. You can say it undoped, or you can say 1E15. This is called unintentionally doped. So I did not try to implant anything. But because of the impurity in the crystal, naturally we have some effective doping. Okay, maybe lower than 1E15, 1E14, right? But we call this undoped. Is that okay? Yeah.
So in that old case, that 1E18 is just coming from your bulk wafer.
No. We do channel implant. Okay, when I say 1E18, I'm mostly talking about region in this here. But your wafer is very deep. Your wafer usually start with 1E15 or 1E16.
So
you need to do channel implant to adjust the threshold voltage. You get 1E18 by channel implant. Okay, so and that's how you get different threshold voltage on the wafer, high voltage, low voltage, because they all have different substrate doping. And you will see that if you try to fit all the curve. Yeah.
So more or less, here's why in that case the channel is low. And here I guess it's really about the magnitude, right? So there's some doping, but we just draw like a threshold that if it's
it is too low just because of the background doping. You cannot get 100% pure silicon for low price.
Okay, so this would be like other isotopes of that.
No isotope. It can be impurity. This is impurity. But how can you have 1E23 atoms per cm cube. Now you're talking about within 1 billion silicon, I only have 1 dopant, right? I only have 1 impurity. It's very difficult to go to 1 trillion, right? Or quadrillion, right? It can be just oxygen or carbon. In the growth process, you do have a lot of this thing. But I don't know, you might actually also have some shallow dopant. Yeah. I don't know, maybe if you go to even lower, that may due to vacancy. This one, actually, I don't study much, so yeah, I don't know, but you do have some, you are right, maybe vacancy, but maybe in the order 1E5 or something, right, very low. Okay, so low that you don't care at room temperature. Okay, now, so compared to bulk, and of course you have a steeper subthreshold slope for FinFET, compared to bulk, you don't have King effect. Why is that? Because it is just fully depleted. Okay, you don't have the substrate resistance, and it's fully depleted, not fully depleted SOI, you don't have King effect. Yeah.
So I guess,
yeah. So you're talking about SOI, right? Not the FinFET. For SOI, you can also dope it. Some people also dope it. Depends on the technology, really. Yeah, but usually we try to, when it is thin, we try not to dope it. And then it depends on the thickness of the film. The film is going to change the, yeah. So there are many factors. But if you try to ask me a question so that you know what technology that you are using, you have, then you better talk to the foundry.
Yeah. So basically, generally speaking, this person, you're employing materials
Yeah,
to do the work function.
it's
rather
a
than
material.
trying to-
Exactly. We cannot use doping to do that. Now, by the way, why we don't want to use doping? There's some problem with doping. FinFET is very small. Go back to do a calculation. If you add one atom to this volume, it probably equivalent to 1E17 already. So you have a lot of variation because one or two atoms can change your threshold voltage a lot. Okay, so that is some interesting thing. Okay, and no impurity scattering when we undope, right? But at low temperature, as I said, Coulomb scattering becomes important. You will still feel it, okay? And also it has less electric field. Let's talk about this. In a bulk device, when it is on, you have the inversion layer like this, right? This is the bending of the band. So you actually have electric field equals to negative dV dx, right? Which is large, right? The gradient of the potential is large. In FinFET, because it is so thin, your gates actually have in from two directions, right? You actually might actually just pull them up and down. You don't have much bending, right? You just pull it up and down through the Fermi level, right? You have some bending. I draw it very extreme, and so this is flat. Then or flatter. Then you have less surface roughness scattering. And sometimes when it is at a high voltage, you can also get something called volume inversion. It's just like what you asked earlier. Everything is transporting at the center. So they're far away from the interface. So surface roughness scattering is even smaller. Okay? Okay, so I want to look at a few papers. Maybe I will only have time for one. Maybe I will just stop at one and then you read the rest yourself if you're interested. It won't be in the exam. This is a pretty old paper, 2009. And they're talking about FinFET, and you can imagine it must be a lousy one compared to nowadays, right? I'm not criticize them, it's 2009, right? Not many university lab can do that, right? But they provide some information I think is good for studying. Now, that is their structure. This is the barium oxide. So is this a SOI or a bulk FinFET? SOI, right? I put it here. So this is the fin. So let's have some feeling. The thickness, the height is 60 nanometer. Although it's not state of the art, but in the right order. Okay. The thickness is what? The width. Did they give the width? I kind of looks W fin. I somehow forgot to write it down. I think it's about 20 nanometer. Okay, sorry about that. You can read the paper. But I want to talk is about the gate step. Just now he mentioned hafnium dioxide. So nowadays, state of the art FinFET is like what? I mean, this is not everyone use the same thing, but it's similar, right? You have the silicon here. You first have something called very thin, only 1 nanometer. Nowadays, it's even less than 1, maybe 0.6 nanometer, 6 angstrom. This is called interfacial layer. I put X because it's non-stoichiometric. It's not SiO2. It's not SiO. It basically is, you can say, some rubbish, but it works, right? It's not a crystal. It's not a stoichiometric or stoichiometric, right? Interfacial layer. Why interfacial? It's between silicon and something called hafnium dioxide. Hafnium dioxide has a very high permittivity. Okay, so I think mentioned earlier, right? Capacitance equals to what? Thickness divided by epsilon. So no, it is wrong, right? What is capacitance? Hey, you're an electrical engineer. Epsilon divided by thickness, right? Epsilon of silicon is like, of course, I can also put the vacuum one, just make it relative permittivity. What's that?
You tell general capacity.
Yeah, per unit area. So it is 3.9. Hafnium dioxide, it depends on your chemistry, but we can say approximately 30. So if I have the same thickness, my capacitance increased by 7 times. Now then you might say, why don't I just make it very thin? I can make it very thin also, right? Together, just make silicon dioxide very thin. What's the problem? Tunneling. It's no longer a good insulator, right? Then you have a lot of gate leakage. And that's why high K dielectrics come in early 2000 in the research, because it scales so fast, you're going to have a lot of leakage. Okay, and then at the end, on the top, you have this tantalum nitride, right, which adjusts the gate function. Okay, so yeah, just a feeling. Then this is the FinFET. It shows how this threshold voltage change of temperature, same as SOI if you remember. Very similar slope will reduce the temperature, then the threshold voltage increase due to 2 reasons: wider band gap and also Fermi level closer to the band edge. You can go back to see that, right? Subthreshold slope, of course, reduced, but remember this is only 150 Kelvin. We are still not at the abnormal subthreshold regime. So it reduces, it keep reducing. It does not has not flattened out yet. Transconductance, of course, increase when you go at lower temperature to higher temperature, right? And this is the fin width. I decided, because of time, not to discuss. And same again, when the temperature reduces, transconductance increases. Maybe I should spend another 10 minutes to do this next time, because there's some equation that are useful. I want to introduce GM over IDS and also maximum GM. Okay, but then I probably not going to discuss paper 2 and 3. You just take a look yourself. Not very important for this class, but important if you want to learn more. Okay, so next class I will talk about the equation a little bit more, and then I will demonstrate a little bit how to do the layout on cadence using the FinFET PDK, and then we go to a new topic. Okay, so let's stop here. Thank you.